So, hello everyone. My name is Thibaut Andrieu. I'm a visualization software engineer at SLB company. So, SLB company is a huge company. It does many things, but its core domain is subsurface interpretation and analysis, meaning we work with geologists, geoscientists, geophysicists to understand what's under the ground. And so the simplest way to understand what's under the ground is just to dig a hole and see what's going on. So that's why we dig a lot of holes all over the world, which are called wellbores. And all along these wellbores, we can take measurements. So we can take temperature, pressure, radioactivity, permeability, and so on and so on. And with these measurements, we can characterize the kind of rocks at a given depth. So this represents a lot of data to visualize. Typically, a wellbore can be up to 15 kilometer length, and we take one measure every 10 centimeters, and there can be 1,000 and thousands of wellbore in a whole field. In this presentation, we will focus on three types of data. The first one is the trajectories. So it's just really the path of the wellbore. So as you can see, it can be vertical, but we can also have curved wellbore. It can even go a little bit up at the end of the trajectories. The second kind of data is the casing. So to avoid the wellbore to collapse on itself, we put tubes, so either in concrete, either in iron, to maintain the wellbore integrity. And the last shape is called the wellbore shape. So this is really the shape of the hole, meaning we have a sensor, a caliper, that will measure the radius of the hole all along the trajectories. And we can visualize it with a color map and also with the shape with a variable radius circular extrusion shapes. Now, a small word about current status in wellbore visualization. So last month, Professor Robin Domicis, which is one of the worldwide experts in geoscience visualization, posted an article on its blog when he tried to visualize 30,000 wells. So on a whole basin, it represents millions of square kilometers. And the important thing is not really the result, but the machine he used to do this visualization. So to load this data set, it requires nearly 150 gigabytes of CPU memory, 50 gigabytes of GPU memory. It uses an RTX 6000. So if you know NVIDIA, the 6000 generally correlated to the price of the GPU. So this is kind of a huge machine. And something to know is that currently the shapes are generally explicit mesh. Meaning from the input data, we tessellate the data and we generate a lot of vertices, a lot of triangles. And this gives us this kind of result, meaning in the current implementation, as we have to generate explicit mesh, the real input data coming from the sensor and from the well log just represent a tiny part of the whole memories. Most of the memory is consumed by the mesh. Whereas what we would like is that the data use most of the memory and only a small overhead is required to visualize this data. And this phenomenon is actually present in various domains, not only in geoscience. For example, if you want to render streamlines in fluid mechanics, or if you want to render an isosurface on the scalar field, or if you want to do a DTI rendering in medical domain, a lot of data viz applications still generate an explicit mesh and still have this problem. So how can we try to improve the memory management of this application? Well, personally, I'm a huge fan of Inigo Quiles, the creator of shader toys, and of distance field and sphere tracing. So for those who don't know this, who doesn't know these images doesn't have any mesh. It's only signed distance field based. And the advantage of sphere tracing and implicit surface is the ability to represent potentially infinite resolution, infinite details, with very, very low memory footprint, as it is just equation. If you render a fractal, you can do infinitely deep with just the fractal equation. So how can we use implicit surface and sphere tracing in our cases? Well, for the first shape, the trajectory, it's quite trivial. The trajectory is actually just a polyline. So we can just display one capsule per segment, and we can easily draw a circular extrusion like this. So this technique is well explained in the literature. It's used a lot to render hairs or fur. I just did a small adaptation. This technique, they generally use as a recast support, the proxy geometry, rectangle billboard, or two cross rectangles. But this kind of proxy geometry can artifact when you look the polyline from above or from bottom. So here I use a small proxy geometry. Oops. Which is a prism, and with this proxy geometry, as it surrounds perfectly the capsule, you can see the trajectory from every angle without any artifact. But there was still a small remaining artifact, a small tiny artifact. If you zoom in at the junction between two capsules, you can see small shading cracks. Why? Because there is a discontinuity in the normal when we go from one capsule to the other. And ideally, instead of rendering a polyline, we would like to render a smooth basis plane, for example. But rendering a basis plane is computationally intensive. And actually, rendering capsule works very well. They're just a tiny artifact at some position. So what we would like is render using capsule, but use the normal as if we add a smooth basis plane. So to do so, when we are on the surface of the capsule, we have to find the closest point in the basis plane from this point and use this direction as the normal. How to do so? So this is the equation of the basis plane. This is just a polynomial equation. And we want to minimize the distance P'. To minimize it, we can start from a position T0 and use minimization algorithm. So how to find the initial position? Well, actually, if we project the point P of the capsule intersection into the polyline segment, this is trivial to do. We have a T0, which is very close to the minimum T of the minimization. So starting from this position, and by doing like a gradient descent or a minimization technique, in just 2 or 3 steps, we can find the point P' and compute the normal, which is completely remove the cracking artifact, as we can see on the left here. So once we have our recast framework and capsule intersection technique, the second shape is the casing. So the casing has a really standardized way to be visualized. So here in the 2D representation, you have the tubes, and you have what the geologist calls the casing tube, which is a small triangle. And geologists are very attached to this representation, so we have to keep it in the 3D visualization. But once we have a recast framework, we can easily do a CSG, computed solid geometry, using interval arithmetic to compute more complex shape. So for example, here, if we do union between a cylinder and a cone, then subtract a smaller cylinder to create the tube, we have the casing. We can even add an optional clip plane, which is parallel to the camera plane to see the inside of the tube. And we have the final shape, which is, again, infinite resolution, infinite quality, and perfectly smooth, and which is direct recast, which means there is no marching loop, so no magical epsilon number or magical maximum step. This is direct recasting. Now let's have a look to the last shape, the most complex one. So the last shape, the Wellbore shape, is composed of the polyline of the trajectories and a well log. So this is the log of the caliper all along the trajectories. And here the idea is to try to create a sign distance field to represent this shape. So I identified a way to have the exact sign distance field, but I can easily compute an approximation, meaning from a point in space here in the figure on the right, from any point in space, if I project perpendicularly this point to the trajectories, I can find the projected point, And from this projected point, I can easily find the log value at this position. And so with this distance, I can find the red distance here on the picture, which gives me a rough approximation of the distance field. So we have the intuition that this works very well as long as the view direction is perpendicular to the trajectories, which is the most case in our application. But problem happened when the view becomes tangential. Because if we use this approximation, we can see here, during the marching step, we take the red line as distance, we go to the next sample, and we miss the high frequencies, so here's the crest. And this is traduced by this kind of artifact in the picture of the right. So how can we mitigate this? Well, this artifact mainly occurs because this is a typical aliasing artifact. Our sampling step is higher than the frequencies of the signal. So if we can clamp the sampling step by the Nyquist frequency of the signal, we can avoid missing high frequencies. So that's what we can do here in the picture of the bottom. If the view is nearly parallel, we just clamp by the sampling, by the Nyquist frequencies. And if the view is perpendicular to the segment, as in the picture on the top, we can see that this clamping is very large. The wavelengths of the signal become very large, so it doesn't handicap the distance estimator we defined just before. So we have the best of the two worlds. When the view is perpendicular, performance are good, and when the view is parallel, performance may be not as good, but the quality is here. We won't miss high frequencies. Now about the results. So the inconvenience of our method compared to mesh-based method is that any ray-based method more depend on the number of pixels in screen than on the same complexities. We can have a very complex scene if all the objects are really tiny on screens at just a few pixels and the performances are really good. So I did the benchmark on the worst possible case. So I create a synthetic scene, as we can see on the screen, with a lot of objects very close to each other and a lot of objects in front of each other. So this is really the worst possible case. This never happened in practice, but at least we will have the performances in this case. And yes, and also everything must be compatible with WebGL because our framework doesn't support WebGPU, so no compute shader, no tessellation shader, no compute in, well, the good old days. And so I did the benchmark on my laptop. So I don't have an RTX 6000, I just have a small GPU with a classical laptop. Regarding memory consumption, so I can save up to several orders of magnitude. So with the previous shape-based implementation, when we reach just a few hundred Wellbores, we reach out of memories. Whereas with this implementation, we can scale up to 10,000 Wellbore before reaching out of memories. And regarding the performances, well, the worst case is similar to the performances we have before. This means in our best case, we can reach hundreds of frames per second, and the vertex shader is no more a bottleneck because we generate much less vertices than before. Now, a small word about quality. In the mesh-based implementation, either we do flat shading, but we see all the triangle and all the ugly shading artifact. Either we do smooth shading, but the smooth shading will average the shading on high frequencies and will flatten all the geometries. But in the right, with our method, we can compute normal much more precisely of the surface by computing the gradient of the distance field, which give much better result than in the mesh-based implementation. And also on the top right picture, here, the mesh were generated using 32 vertices per circle, and we can see a bit the tessellation, the classical tessellation artifact, whereas in our method, as it is an analytic surface, the surface is perfectly cylindrical, perfectly smooth. There is also some goodies that weren't anticipated at the beginning of the development, but if we just enable the MIP mapping on the log values texture, which is a 1D texture, we directly have a mip mapping mechanism on the color, but also on the shape, on the surface. And if we change the interpolation of the texture, if we change from nearest, linear, or cubic in the picture on the bottom, the algorithm directly adapt to the interpolation without the need to regenerate something else to adapt the algorithm. As it just takes the values, it directly takes the interpolation which is currently configured. Unfortunately, there is still one big limitation. As this is based on ray marching, we have a loop with a max step to avoid infinite loop or to avoid too long array. And if the loop stops before the ray reaches the surface, we have empty space, and this is traduced by this kind of artifact when the view is tangential to the trajectories. So idea for the future, so I have implemented the really basic implementation of sphere tracing, but now there is several optimizations that can optimize the performances and also mitigate the artifact. As if the sphere tracing is more efficient, I can do an array which is longer and maybe limit the artifact described before. Another easy optimization that I can do in the top right picture is currently I take the same proxy geometry for every segment of the polyline. But if I can find the minimum radius in every segment, I can create a proxy geometry which is closer to the actual surface and improve the performances, limit the empty space. And also another idea in the picture on the bottom right is to use the mip map of the signal by computing not the average of the sample, but the max value of the sample, which will give me some kind of quad tree, not really a quad tree because it's a 1D signal, maybe it's a B tree, I don't know how to call a tree on 1D signal, but I can probably use this structure to accelerate the signal and go straight to the surface. So now a video of what it gives in a wall scene. So this is synthetic data. Unfortunately, I cannot show you real data, but it looks more like this. We have a field with lots of trajectories. So in this case, we have 20,000 trajectories, 400 casing, 200 Wellbore shape, everything resident on the GPU, no startup time. We directly take the data, send them to the GPU. And we don't have to load, unload, depending on the point of view, as it uses only 150 megabytes. We can put all the data in the GPU and then just navigate on the scene. So that's it for my presentation. Thanks for listening. And now, if you have any question, I will be glad to answer them.
Questions? Got one there.
Hello. Okay. Thank you for the presentation. I was wondering, is it only for visualization, or with these data you also need to do like some simulation stuff, some processing, like heat diffusion or something like that? And if so, since you have like SDF representation, maybe you could have gain on that side too with Walton sphere method and such? I don't know.
Maybe currently I just take the data and send the data straight to the GPU. I just do a decimation of the trajectories because I have one position every 10 centimeters. But if the trajectory is vertical, I just need 2 points. But that's the only filter I do on the data. I don't compute anything else. The idea is really to take the data, stream them to the GPU to have the shortest startup time possible.
Okay, well, thank you.
So as someone who's sort of outside of maybe a lot of the expertise of people in the room, are there other challenges that you have that would be interesting for a community like us to solve?
For geoscience? Or?
Yeah.
Yeah, for geoscience. Yes, in geoscience, there is two kind of data. So this is a wellbores, but there is also seismic data. And seismic data is a huge volume of data. And a seismic data set can represent up to 100 of gigabytes, up to several terabytes for one data set. So they are currently rendered in volume rendering using octree, tiling, and loading and unloading. But yes, this is a complex challenge because of the amount of data, and we don't have the money to buy an RTX 6000 to every geologist. So yeah, if some people have challenges in large volume rendering, I would be interested.
Other questions?
Thanks for the presentation, and I am also a fan of Inigo Quiles. I wanted to ask about is the curvature important here? The curvature of the shapes?
Of the trajectories or of the Wellbore shapes?
Both.
Both. The trajectories, it's the curvature is quite smooth as it's a gelling device. We cannot do 80 degrees curved, so we have a curvature radius of maybe few hundred meters, few kilometers. On the Wellbore shape, I don't really know what do you mean by curvature of the shapes.
I mean, I am asking this because, so if when you're doing the ray marching, are you using like a uniform step? Because maybe you can adapt the step depending on the curvature. You know, like if it's plain, you can do a bigger step. But if it's a high curvature, you need more precision, so you can adapt the step of the ray marching.
Yeah, exactly. I thought about this because when drilling, for example, if you drill through something strong, through granite, for example, the shape will be quite smooth because it's a solid rock. But if we drill through sand, the sand may collapse, and here we will add a lot of curvature. So there may be area which are quite flat. So in this case, as you say, we can do large sample step, and on more high frequencies, we could reduce the step. So yeah, I think this will be beneficial in this problem.
Thanks.
Any other questions? All right, if not, let's thank our speaker again.
Thank you.